Welcome everyone. I'm Márton. I'm from Hungary. I have a master in structural engineering, and I'm from a design firm called BIM Group. And we were approached by a University of Hungary, Corvinus University, by Orsolya Nagy. They wanted to do a research on the project that we worked on the realization. And at the end, she couldn't attend this conference, so I'm presenting in her name as a co-author and as a project participant. Okay, so our research is about finding connections between C4 construction 4 technologies and their effect on achieving sustainability development goals. And we took a newly built project, which is already realized in Hungary, Budapest, and investigated the technologies used in this project and tried to find the connections on achieving the SDGs. The case study is focusing on this stadium. It's an athletic stadium in Budapest. This will be the main venue of the World Athletic Championship this August. It was built by mainly Hungarian companies, and the research focuses on the roof structure. It's a rigid steel structure with a pre-stressed cable net. And this structure was built by a company called Case Group. Case Group is a major operative on the Hungarian market. Primarily, they work in the construction industry. For 40 years with 2,500 colleagues. They have a big responsibility in the Eastern Central European region. The methodology that's used for the research is a qualitative research methodology, where we took a case study approach. The research can be broken up to 3 different phases. In the first phase, the design of the research, there was a kickoff meeting with project participants and management team. During this meeting, we were exploring the innovations that were used in the realization of this project. And already in this meeting, it was outlined that one of the major innovation was a large volume matrix of the steel elements. After this followed by the case study itself. It consisted of several interviews and workshops with the project participants. During this, the innovations were explored in details. These interviews were conducted with key project participants from manufacturing, construction, measurement, management, cable specialists, the key people of the project. And in the last phase, there was a literature overview on sustainability development goals and the possible evaluations. And then the case study results were challenged against these methods. So about the challenges, the project was a very complex project for the companies involved. And the participants summarized their main challenges as the followings. For the design team, being a pre-stressed cable net, which is relatively flexible, it results in big movements. Different stages of the construction resulted in different geometry, and this had to be handled accordingly through the BIM model. For the manufacturing, the key challenge was geometrical accuracy, which was 3 millimeter on 10, 20, 30 millimeter 30-meter elements, which is really, really tight. For assembling team, movement of these big elements and positioning of the base assembly, which receives the entire steel structure. And for the cable installation, it is very sensitive to the geometry. So from the perspective of cable installation, both rigid steel and cable geometry was a key parameter. And to solve these challenges, DfMA-oriented parametric-algorithmic design method was chosen with the combination of the LVM technology. So following the 4 main stages of the project, the first is manufacturing. It is modeled on the geometry is modeled on a stress-free state of the steel elements. It's modeled in Tekla structure. It has direct connection with the cutting machines through numeric data. The welding of the assemblies is quality controlled by laser tracking measurements and 3 different levels. And because of the size of the elements, the temperature effect had to be compensated as well. During the assembly, the compression ring was broken up to 48 so-called diamonds. These have a size of a 10-level block building. So it's quite big and about 70 tons. And all the manufacturing error was compensated on the adjoining element. The error was summarized, and the base assembly was positioned with the negative of this error to reduce the inaccuracy of the compression ring. When the full compression ring was erected, a final total station measurement was done to prove the geometry of the compression ring. After that came the cable tensioning. This is a very complex process done by specialist companies. It's fully automated, computer controlled. It has a very detailed lifting sequence, which is based on finite element calculations. There are 3 main stages. First, the upper cable system, then the lower cable system, then joining the 2 cable systems together. And that is automatic quality control. They measure hydraulic jacks based on the pressure. They can calculate forces and also the movement of the cables. And also there is total station measurements from the field. And finally, when the primary structure is built, all the additions go on the structure, secondary structures, purlins, LED screens, gantries, equipments, MEP. And then the full roof is built. This is the so-called equilibrium shape. And this is the final geometry, which is actually represented on architectural drawings. So all 40 stages, it is a different geometry. And for each stage, an appropriate BIM model was generated with the algorithmic approach. Benefits of these innovations. BIM and DfMA-oriented parametric design requires very strong cooperation between project participants, and it also strengthens this cooperation, and it can result in very efficient solution. These participants work together on previous projects, and some of the methods were already piloted in previous projects. So these innovations could be considered in the tender period already. Having the tight accuracy on the steel structure resulted omitting of trial assembly of these diamond elements, which would be very time consuming. This significantly reduced the manufacturing time and also reduced on-site activities. The cable lifting was an automated process, which was very fast. It took about a month to lift up this cable net. And the force deviations were about 1 to 2%. And also, again, the tight tolerance on the compression ring resulted in only 21 millimeter on approximately 800 meter length of the compression ring. And as the research showed, even though it was not a primary objective, these innovations, these technologies contributed to sustainability development goals. Approximately 20% of the steel material could be saved, which relates to responsible consumption. Less raw material was needed, for which less water was needed, which correlates with water. And also because of less material, the carbon footprint is smaller. It is helping number 13. Yes, number 9 is about using innovative technologies. So it's also the technologies that I mentioned before. Sorry. Yes, and because of the savings, there is also financial savings, which relates to economic growth. And for summary, I would like to highlight four points. One, that in these complex projects, we already have technologies that can be used. The industry players should take these technologies. And if they use the right tools, it will save them significant time and significant costs. It's also beneficial that the design requirements are met and it improves structural quality. And not the least, sustainable development goals are also achieved. And I would like to add that for now it's subjective, but we would like to continue the research and try to quantify these relations between the innovations and their effect on sustainability. And thank you for your attention. And I'm very honored that I could present here to you today, and I will try my best to answer your questions.